afternoon, everyone. So I'm Ingo Ludtke. I'm head of power electronics at the Catapult. And I would like to speak about device modeling and the automation of simulation for power electronics design. So first, a brief word about the Catapult. The Catapult has been around since 2018. We work on collaborative R&D projects with the UK industry to help the industry introduce compound semiconductors into their products. So compound semiconductors, as we heard, relates to wide bandgap components. The Catapult is not designing or assembling these components, so we are technology agnostic in a way. So we would take silicon carbide, gallium nitride, gallium oxide, or even aluminum nitride as input, and would package and put the packages into solutions. So our vision is ultimately for the UK to become the global leader in the application of compound semiconductors. That sounds very bold, but there is good reason for that. The UK has great strengths in academia and also in the manufacturing of these technologies. This is the slide about the motivation for the net zero and the need for power electronics conversion. So obviously the big sectors as in energy and in industry and also in transportation, they all rely on power electronics conversion to improve efficiency. And the power electronic conversion needs to become more cost effective to be more widely applied in those areas. And that combined can drive down the emissions and also increase the adoption of power electronics converters. So you see there that the overall market can be up to 46 billion by 2028. So the compound semiconductor materials have great material properties that ultimately improve on conduction and on switching losses. So that's great. There are some limitations in terms of the widespread use, and the main aspect of that is that the cost is higher than for silicon. So this is kind of offsetting the adoption of compound semiconductors quite a bit. And what we found is that in applications that use batteries, there is the scope to easily make up for that additional investment, because the batteries are so expensive that any improvement that leads to a reduction in battery size can ultimately justify the use for compound semiconductors. And that is why silicon carbide, for example, has been so successful in the EV sector already. So the two middle branches on this slide, they are the areas that the Compound Semiconductor Catapult focuses on for power electronics. We design, prototype, assemble, and test power modules and power converters. And what we are doing there is basically benefiting from the material properties to design systems that give advantages in the final application. So what we found from over 20 collaborative R&D projects over the last few years, and not only in the automotive sector, but also in some other sectors, is that the design of power converters and power modules is very complex and is more complex than it is for silicon devices. And the reason for that is that the power semiconductors are becoming smaller. The solutions overall are more power dense, and the coupling of electrothermal and electromagnetic and even the cost aspects of the final solution is much bigger. So what we are trying to do is to move from a scenario where 80% of the design time relies on prototyping and prototyping tests, is to move to a scenario where we turn that around and do a lot more simulations. And that can give a lot more optimization ultimately and allow to reduce cost while maintaining and fully exploiting the advantages of wide bandgaps. There are some limitations in that approach, obviously, which I will go into. First of all, the existing design tools from the various vendors, and we've seen a few today. They are fantastic, but they tend to sometimes only cover certain areas of the design. So as a power electronics designer, you end up using one package for this and another package for something else, and then you have another investigation and you need to use another package again. That makes the overall design process quite fragmented and difficult. So what we are hoping to do, but this is not very straightforward, is to combine the high level of complexity of power converter design and the multiple objective requirements that are needed to minimize losses, weight, efficiency, and cost, for example, into a system that relies more on modeling and simulation to simplify and optimize better. So here's a very simple powertrain scenario. You see on the right-hand side a propulsion motor driven by a power electronics inverter, fed from a battery and charged from a battery charger. And in between, for this particular market, there was a fuel cell. There is a power electronics switch. So this switch is sometimes called a solid-state switch or a solid-state circuit breaker. So it's a very common power electronics element. The beauty of this one is that it is relatively simple. So its job is to switch on when needed and to block voltage in the reverse direction. So there should never be any energy flowing from the battery charger or the bus system that is in front of it to the fuel cell. So with that simple scenario, we have investigated what can be done to automatically optimize. And when looking at the switch scenario and thinking about the switching and the blocking part separately, we've allowed up to 6 different discrete semiconductors to be used on a heatsink. So we only have sort of 7 places to fill and have a very limited set of candidate components that could be used. So these candidate components included silicon IGBTs, silicon carbide MOSFETs, and also for the blocking part, silicon and silicon carbide diodes. So going through all these permutations, we very quickly found that there are over 25 million different combinations that could be used. And obviously, when simulating that with a traditional SPICE-based, Saber-based, or Plexim-based simulation, that would take approximately 2 seconds per run to execute. So that would take obviously too long and would never be done. That's one of the problems. What we also found in the process is that even for this small set of power devices, there is quite a variability in model availability, in model scope, in model accuracy, and sometimes discrepancies between data sheet and model. So all of that combined puts a little bit of uncertainty into the models that are being used. So what we've done through this study is to try and find ways to improve the models and also to reduce the simulation time. So we got rid of the SPICE-like circuit simulation by implementing the solution directly in a programming language, and also have remodeled the models from their SPICE description into equations that could be put directly into the programming language. So what that enables is to go through all the combinations and then come up with a plot as shown here, which shows the material cost versus the power loss. And in this colored area there are nearly 9 million different combinations and solutions. And that area shows the range of possibilities in that it's quite easy to pick a very inefficient and very costly design when not using the right components. But when using the components that correspond to the Pareto front, companies can decide the sort of value that they will provide to customers. So they can come up with a scenario where the inverter is very efficient at a slightly higher cost or less efficient at a lower cost. So companies can pitch where they want their market to be. To do this in a wider scale would require two phases. One is to create more accurate models, and the other one is to create optimized systems from automatic simulation. So we've got an internal project going on at the moment that is trying to implement this. So we have got fantastic characterization facilities in the Catapult that can do the static and dynamic, electrical and thermal characterization of components. We have got, together with Cardiff University, the ability to use artificial neural networks to model that characterization data. We are putting this into a library of components from which then a multi-objective optimization can take component combinations to ultimately come up with optimized systems. So that has been partially verified now by using various case studies that are indicated here. So we have a few other projects going on that benefit from this background work. So here's just a snapshot of what is involved in the characterization of wide bandgap components. There is various inputs. In this case, it can be modules, discretes, or wafer of components, and they are analyzed using static and dynamic electrothermal instruments to create data that is then modeled. And ultimately, these ANN models are implemented in SPICE or in Verilog directly, so they can be run transparently in a wider simulation. So here's more detail on that process. So there's a lot of waveform data, many gigabytes that we have accumulated of various components to take us to ANN models of these. And then on the converter level, here's a study for reducing the computing time for a DC to AC converter as it's used in photovoltaic systems. Again, a similar approach in that the outputs from a DC-DC converter or DC to AC converter in this case can be modeled according to the combinations of components that are used and operating frequencies, and those models are then used as a proxy for a longer time simulation to arrive at a multi-objective solution to minimize size, volume, cost, reliability at the same time. So our vision is to automate power electronics converters by having faster design cycles, ultimately having a better product at a lower cost. And we need to do that through better power device modeling, optimizing the power converters using those models, and ultimately feedback from prototypes that this kind of loop improves over time. Thank you very much.